Okay, so topic basically polynomial functions. A lot about their graphs, the behavior of them. Okay, so, and again, we're going to do a lot of stuff on Desmos, but then I'll try to summarize it all on here. So, first of all, there's a couple different forms for polynomial functions. Okay, there's what we call a general form. Which would be something like this. Okay, so what does all that mean? Well, that means that you would have A, B, and C are just regular old real numbers. So we have 3x like to the fourth plus 2x to the third plus 3x to the second minus 4x plus 8 would be an example. So see, basically, these are all your A, B, and C. K is a constant. Those are all just numbers. This power could be, any number, right? And then you just write it one less. This is called decreasing order, right? You probably picked that up someplace else. So that would be one example of a polynomial function. They could be as simple as a line. Okay, that's a polynomial function. And they could be as simple as just a 10. Right, that's a polynomial function, because it could just have a constant. All right, so they encompass a wide range of functions. Okay, all right, a wide range. The only thing that they don't take into consideration is stuff like the piecewises that we did, and the square roots and all those things. Okay, those are different. So what we want to do then is take a look at these polynomials functions, get some characteristics of their graphs, and then we'll kind of progress on from there. So one of the things they want to do is also solve these. That's where we're working towards too. Okay, so anyhow, let's do this. That means there could be more, there could not be anything. I mean, it just goes to a constant.
So is general form just then in a line decreasing?
Yeah. Well, it could be decreasing. Properly, it's supposed to be written that way, but if we mix the terms up, it's still general form. Okay? Okay, so that's general form. There also can be written in what we call factored form. Okay, so here we would have C1 and C2 and C3 and etc. are your x-intercepts. Okay, and A is just some number there, real number. So that's the other form. All right? So there's general form and then there's factored form. And to get from this form to this one, we just have to multiply all this stuff out, like FOIL it, or whatever you want to think about it. Okay? The factored form tells us a little bit more about the graph of what this thing looks like. So in other words, if we were given something in factored form, for example, all right? We know a little more about this type of a graph than we would the other one because we know that these are the x-intercepts. And it's always the opposite, right? It's always the opposite of those. Okay? So those are the x-intercepts. So those are the two ways we can write a polynomial function. Either in general form or factored form. Okay? All right. So let's go into Desmos and let's play around with some of these graphs, and I'll show you some stuff that we're going to know here. So I'm going to have to switch to this. Okay, so let's graph some in factored form. All right. So, and you can go f of x here, or you can do, or you can type anything at all if you don't want to, but y equals, I think I'm just going to go parentheses x plus 2, and I'm going to start out fairly simple here. Okay, so let's just start with this one, all right? So we know this is going to make your quadratic or parallelogram, right? X-intercepts -2 and 3 come from the -2 and 3, okay? At one point, I think we said something about this was decreasing here. Do you remember doing that? Okay, increasing, okay? All right. Absolute minimum. This is some stuff that we've had before. Okay. X-intercepts. This has a degree of 2 because if we FOIL this out, we're going to get x squared, and that's the highest power. So this has a degree of 2. Right? And it's a nice U shape. Okay. There's one other idea about the polynomial here, something called end behavior. So end behavior is what's happening at the end of the function, okay? So like as this thing is growing up this way, and at the very, very end over here, we say that it is increasing because as x approaches negative infinity, we say that this graph is increasing. Same thing on this side, as x approaches positive infinity, we say that it's increasing. So increasing, increasing. All right, that's called end behavior. I'll summarize all this stuff too on the tablet, but I said, first we got to do this kind of thing so we visually see what's going on. All right, end behavior. End behavior is different than what we had before. We talked about intervals, and that way we're going left to right, whereas end behavior is looking at it this way. Okay, so it's a little bit different. All right, that one we've seen before. So I'm going to turn this off, come down here. Well, actually, just add another one to this. So we'll go parentheses, x, let's go plus 4. So we'll put one on the end there. I'm going to turn this back on. And now we have what is called a third degree polynomial, because if I FOIL this out, I'm going to get x to the third. This is a third degree polynomial. X-intercepts at -4, -2, 3. Okay? We have let me get a little better. There we go. All right, so We talked before about intervals, increasing, decreasing, increasing. Max, min, relative to the local, right? Because they're not absolutes. And behavior is falling down. So as we go towards negative infinity, it's falling down. This one's going up. So it's sort of like this kind of deal. All right, so we say in behavior as x approaches negative infinity is decreasing, positive infinity increasing. Right? And we have what is called like an N shape. N. All right. So we're kind of getting some ideas here. Let's try. I'm going to go ahead and let's get another one. Parentheses x minus 1. All right. And I'm going to put a number out in front of this. Oops. There we go. Okay. Fourth degree. Why? Because I have 1, 2, 3, 4 powers for the x. Okay? Fourth degree. There we go. Intervals decreasing. Here's a couple minimums, right? Relative, local max, and behavior. Increasing, increasing, going up. So we got this again, all right? If I was to get this just right, so let's see, I want to take this and make this. There we go. So if I do this just right with my window, this doesn't look like a W anymore. It looks more like a U. Okay? So that's a fourth degree. So I'm going to go back to the normal thing. I'm going to come back up to here. I'm going to do one more. Okay. And I'm going to make this. Try 1. That's a little better. All right. So now we have something that looks like this. Okay. And this would be my fifth degree because obviously on the 5-axis, if I power around. Okay. And behavior, decreasing, increasing, 5 x-intercepts all over the place. Okay. But if I made my window just right, I would get something that looks like this. Okay? So we should start to see some patterns that, wait a second, if I have a odd degree, then I'm getting something like that. I'm going to get something like that. Okay? Okay, let's do this. I'm going to put a slider in here. Now I'm going to eliminate some of these. I don't need so many. Okay, that's not too bad. We don't need a parenthesis there. There we go. All right, so let me get back to this screen. Okay, so I put a little slider in here, all right? And I want to see what A does. So as I change that A value, what's it doing to that? Okay, so here's what happened with these. First of all, let's talk about the degree. So that's the highest power of the polynomial. So if it's written in general form or factored form, it doesn't make any difference. So whatever that highest power is, that's your degree. So for example, x to the third plus x to the squared plus x plus 4, that's a third degree. And if it's like this, that's a third degree. Okay? Even if it's written like this, which we haven't looked at yet, that's a third degree because this one is written twice. Okay? So that counts as 2. 1, 2, 3. Okay? So that's a third degree. Those are all third degrees. And then, of course, if I have an x to the fourth, even if I skip a term or two, that's a fourth degree, highest power. Another fourth degree. Again, because we have the two twos. Okay? And this one here you can fill in with anything you want. Fourth degree. All right, so the degree is the highest power. So that's important because that helps us name them. All right? So third degree, fourth degree, fifth degree, sixth, blah, 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 blah. But here's what's important, is what we said here. If we're going to have an odd degree, then we're going to get something, it's going to look something like that. Okay? Even if it's a fifth, it's going to look like that. Okay? Even if it's a fourth root where we get a W, okay, at the right window, it's going to look more like a U. Okay? But notice this end behavior here. So what's the end behavior of this one as x approaches negative infinity? What's it doing? What are these doing? Up or down? Which way are they going? Falling down. Okay, so as on the negative side of this, they're falling down. What are these ones doing on the positive side? Increasing, right? What are these doing? On the negative side, it is increasing, and on the positive side, it's increasing. Okay. So the end behavior here, here's what we're going to say. All right, so as x approaches negative infinity, it is decreasing or falling, it's going down, okay? As x approaches positive infinity, it's increasing. What's happening at the end? That's what end behavior is all about. In this case, as x approaches negative infinity, it's increasing, just like you just said. As x approaches positive infinity, it's increasing. There we go. Let me shrink this down a little bit so you can see it. All right? Okay, so I'm going to go back to Desmos now, all right? I want to take a look at this. So I'm going to get rid of this, Okay, so I'm going to type in a new one here. Y equals, notice I'm doing everything in factored form, plus 1 parentheses x minus 2 to the, and I'm going to put an n in there, and I'm going to add a slider. Okay, so what I'm doing is I'm setting up an x plus 1, x minus 2 to the n, and I'm letting n equal 1, 2, 3, and 4, and I want to see what that looks like. So here, nothing exciting there, because n is just 1. That's a U-shape, second degree polynomial. Now I'm going to move this to 2. Okay. See, well, that's nothing exciting because we just covered that. 1, 2, 3. Cubic. All right? What are the x-intercepts? -1 and 2, right? Nothing changes, but wait a second. When we had a cubic before, like this, how many x-intercepts did we have? 3. How many we got now? 2. Okay. Because what did I change? I made this a 2. So what's happening here at 2? Does it cross it? It's just touching it, isn't it? And it's bouncing off. Okay. When you have a situation where it comes down, touches, and bounces off, that's called a double root. Okay. In the book, and in other books also, they call that a multiplicity root. Okay? And they say that has a multiplicity of 2. Why? Because this is square. So So that gives you a multiplicity of 2. All right? But there's some important information here that we're going to talk about kind of all at the end here. It'll all come together for you. All right? And this only has 2 x-intercepts. All right? This is a 2. Okay. So now I'm going to make that a 3. So now that's going to change it so that we're going to have what kind of a degree polynomial this time if I make that a 3? What would the degree be? Okay, think about this now. So this is 3, right? What would the power be on the x if we multiply it all out? Okay, it's Saturday morning, Memorial Day weekend. All right, we're all going, wake up a little bit here. Okay, this is 3. This is 1. What's that give us? 3. Plus 1 is 4. There's our magic number, okay? 4, right? So we're going to get a 4th degree. So in our mind, we should know, he said that a 4th degree is going to look something like this, or W. Okay, so here's what we should, this is what we should get. There it is. All right, but wait a second, that doesn't look at all like a W. Maybe one I made when I was like 3 or 4 years old, I thought I made W, okay? But here it is. There's our x-intercepts. -1, and what's the other x-intercept? 2. Yep. It is, it's 2. Here we don't have a double root because it's not touching it and bouncing off. It's going through it, okay? But if we zoom in a whole bunch, it's flat. It's really flat there, okay? So that means, yeah, it crosses it, but it's pretty flat when it gets to it. And then it finally crosses over. I mean, even Desmos doesn't do a really good job of drawing it. See how the line, the curve is actually above it. It looks like it crosses right about here, but in actuality, it's supposed to cross it too. Okay? So that one they say has a multiplicity of 3 because of this power here. Okay? But you wouldn't really know it. Yeah.
So would 2 still be an x-intercept?
Yep. Yep. It's still an x-intercept. It's just Desmos doesn't do a very good job of drawing it. But I think if you click on it, see it goes right to that 2 and 0. If you come over here, see how it has a negative 0.001? But I swear it looks like it's above the line, right? But right there, 2 and 0. Okay? It's just a distortion. So say it has a multiplicity of 3. Okay, it's going to go through it. All right. I'm going to go back to the house here and get a better graph. Okay. Here we go. Changing it to 4. So what would the degree be? We'd have 4 here. 1 here. So what are we going to get? Highest power, 4 and 1 give us 5. Okay? There it is. I'm going to zoom out a little bit here. I think I get to this there. Zoom out a little bit. There it is. Okay? In this case, same thing. Coming down, it bounces and goes back up. Okay, that's a multiplicity of 4. Does it cross over it? Or does it just touch it? What do you think?
Just touches.
Just touches. Okay, it's just touching it. Okay, but if you zoom in on it, like we just did on the other one, guess what? It's going to be real flat there. See how flat it is? It's the same thing, all right? It's just that it's flatter. So those are called multiplicities. In the case, or in the case of the 2, it was called a double root because it's counting it twice. Okay. In this case, I don't think I've ever heard it called a fourth root. Most of the time they just talk about its multiplicity. It has a multiplicity of 4 there. Right. But again, you should see a pattern in if we have an x minus, say, c is my x-intercept, and this is an odd number, okay, it's going to go through the graph at c. So I'll just say something like this. It's going to go through it. It's going to be flat there, but it's going to go through it, okay. If it's an x, and I'll write this on the tablet, x, and it's an even degree, then at c, it's going to bounce off, okay, like that. It could be flat there, but it's going to bounce off. And those are called, like I said, multiplicities, all right? So let me go back to here. We'll put that on here. All right, so if we have y equals x plus 1, and then I go x minus any number, it doesn't really matter what it is, okay, and I make that an n, all right, n is odd, it's going to pass through the 3, okay? So in other words, right here at 3, it doesn't really matter what's happening in these other places, okay? So this would be like a plus 1 that's going to pass through it, okay? Pass through that. But if n is odd, or excuse me, if n is even, then it's going to bounce off. So that's the deal with that, okay? Those are called multiplicities. So you're going to have you can have a multiplicity of whatever that power is, okay? So for example, if we have x plus 1 and x. Oh yeah, sorry, I'm sorry. I don't know how I did that. Here, let me go back so you guys can see it. I'll just kind of stop all. Why is it not showing up here? Let's try this. I'm writing away here. There we go. Let's try that. So, x plus 1 minus 3 to the n power. Okay. N is odd. It's going to pass through it. Okay. It's going to pass through it. It doesn't matter what's happening out here. We're only interested in this part of this right now. Okay. Passing through it at 3. Okay. It could be flat there. Here, x plus 1, x minus 3 to the n. N is even. It's going to bounce off of it like this. Okay. Again, you can have as many things as you want, but that's what's going to happen there. It's going to bounce off of it. It could be flat there. It could be. Then here we have a multiplicity of power is the power of it. So if I have here, say I have a 2, then we would say that has a multiplicity of 2. Okay. If it is a 3, then we say it has a multiplicity of 3. And that's all they have on that. Yes. Yeah. Well, you could have a graph. You could have a graph like this in general form. However, you wouldn't really be able to figure out by looking at it what the multiplicity is. So, for example, if we have something like this, I wouldn't know if that has a multiplicity or not. Okay, I can't tell. But as soon as I put it into a factor form, if I could, then I would be able to tell because I'm going to get this thing here. Okay.
What if there's more than one and it counts that?
Oh, so you're saying, well, could you have more than one multiplicity then, right? Let's take a look at it and see. So let's switch back here. That's a good question. Let's try it out. That was nice. Okay, so here is a 2 and a 3, right? So what's the degree on that? Yep. So here's our double root, right here at -1, our multiplicity of 2, right there, comes in, bounces off. Here's our multiplicity of 3, right here. And we're getting a fifth root, okay? So if I zoom out a little bit, see, if we zoom out just right, you won't even see that little glitch there, and it'll look just like an N.
So what's the multiplicity?
So the multiplicity is whatever the power is here. So here, we say the multiplicity is 2 because it's at x equals -1. That's the 0, or the x-intercept, and the power is 2. Right? Here, this is at 2, okay? The power on that is 3, so we say that has a multiplicity of 3. And that's it. So whatever this power is what they call multiplicity. Okay.
And that's the degree is 5, and then the multiplicity you stated separately? Or the multiplicity would be 2 and 3, or is the multiplicity 5?
No, the multiplicity is 2 at this point and 3 at this point.
Oh, okay.
But the degree is 5. Okay, so let's do some here, let's go back to this now. Okay, so let me do some kind of problems that you're going to see here. So let's say here's some they're going to want you. Here's some things that I'm going to ask you to do on the final and that they're going to ask you to do. State or list, they're going to call them zeros, and multiplicity. Okay, that's one thing. They're going to talk about x-intercepts. They want you to list those. Okay, they're going to talk about turning points. We haven't mentioned that, but that's really, you'll not have any troubles with that. And behavior. Okay, so going to give you some polynomials, all right? We're going to look at them and answer those questions. They could be in any form, all right? So let's do some in both forms. So number one, here, let's do one like this. Okay, oh, also let's they don't ask you, but I want to put degree down here. And degree. Okay, we'll toss that in there too. Okay, so 4 things. Zeros, multiplicity, x-intercepts, excuse me, turning points, and behavior, and degree. Okay? So, what's the degree of this? First of all, let's just look at it. What is it? 3. Okay, that should come real quick. You should be able to scan it and say, 3rd degree highest power, right there. Got it. Okay, degree is 3. State the zeros. What's the only way we can figure out what the zeros are? Yep, you got to put it in decimals and graph it. Okay, there's no other way that we know right now we can find zeros. We got to graph it. Okay, so go ahead, type it in. Tell me what the x zeros are. Now remember, the zeros, x-intercepts. That's what those are. So x-intercepts and zeros are all the same. So type it in, and let me know what the x-intercepts are. Or the zeros. They're the same thing. They're not going to be nice numbers because I just made this up. Negative 3.533. Okay. That's the only one? Okay. That's the only one. It's possible we're only going to get one. So that's also the x-intercept. Okay. Turning points. I better take a look at this now. Here, let's do end behavior before we do turning points. So as x approaches negative infinity, you should know what the end behavior is without even graphing it because it's a 3rd degree. And we know from our work what it is. But maybe you want to graph it anyway. So what's the end behavior as x approaches negative infinity? It's either going to fall or it's going to rise. What's it going to do? Decrease. As x approaches positive infinity, what's it doing? Increase. Good. Turning points. So what I'm going to do is go into here, and I'm going to graph it, and we'll talk about turning points here. Come on. Get rid of that. I'm going to type it in. Y equals x to the 3rd.
Are those the local mins and maximums?
Yes. But it's just asking you for how many there are, not what they are. Okay. So in this case, we'd have 1, 2 turning points. 1, 2. That's it. So we have 2 of them. Okay. turning points are just a number, so if you're going up here, kind of like a roller coaster, you hit the top, right? That's 1. Coming down, here's the bottom, that's 2. So it's just got 2 turning points.
So just like the locals.
Yeah, but it's not, yes. But you don't have to say what they are, you just say how many there are. So 1, 2, 2 turning points. 1, 2. That's it. Okay, 1, 2. That's it. So going back to this. I would say zeros, there it is. X-intercepts, got it. In behavior, let me note that. Turning points. Two. 1, 2. 1, 2. Okay, that's it. That's all you gotta do. All right, you don't have to say what they are, you just say this is what it has. All right. Let's do one more and then we'll get you a break here. So let's try 1 this time. Okay, so here we go. Now, can you tell the zeros and x-intercepts by looking at this one without graphing it? Can we do that? Somebody tell me that. X-intercepts and zeros without graphing it. -3, -1. Very good. So you don't have to, so when it's in factored form, see, you know it, right? You don't have to graph it. That's what's kind of nice about it. -3, -1, and 1. Okay? There, we got that done. Any multiplicities on this case? Do we have any multiplicities? 2, where at? What x-intercept? Okay, so -1, there's a multiplicity of 2. So I'm just going to go mult of 2 at -1 because there's where my power is. Okay, so my x-intercepts and zeros are there. Okay, I have a multiplicity of 2 at -1. So in my mind, I should kind of have an idea what this looks like. And we haven't graphed it yet. Okay, so we did that. What about the end behavior? Let's do that. End behavior. So, what's the degree of this? 4. 1, 2, 3, 4. 4th degree. So, now that I know what the degree is, right, I should be able to come up with the end behavior. So what's the end behavior of this one? As x approaches negative infinity, what's it doing? Increasing, good. X approaches positive infinity. What's it doing? Increasing. Good. So we didn't even graph that one, and we could answer all the questions just by looking at the equation. So see, it's easier when it's in factored form than it is when it's in general form. You can't tell a whole lot. You have to graph it. Factored form, we can deal with that. So there'll be most of them in here are in factored form, and then they have a lot of graphs. But they could be in either form. Yeah, there are some in general form. Okay, so let's take a about 10-minute break or so, and then we still got a few more things we have to do in this section before we move on to the other one. So also, there's another one here we can take a look at. You can just set it down, that's fine. Not just one.
Okay. I'm sorry, you said set it down where?
Right, on that. You can set it either table or by the stapler, that'd be cool. Start a stack up.
And then the homework isn't due till next week, right?
Right.
No homework today.
Nothing. Nothing turned in today. So if you have something like this, okay, this is a little different than having the power outside. Okay, so don't get this one power confused with one that's going to be on the outside. So this kind of messes stuff up a little bit for us. So we know that one x-intercept and 0 is 3. But this kind of messes things up. So maybe I need to kind of graph that a little bit and see what's going on. Okay? I can still tell what the degree is. What's the degree of that? Three. It's still a third degree because you have 2x squared and an x. So it's still a third degree. The question is, oh, and that x squared kind of messes me up a little bit. All right, so let's go and graph it. Okay, so here's what I got. All right, so third degree, going to make it n, okay? X-intercept at 3, makes sense. I don't have any other x-intercepts. The reason for that is because, if we think about this a little bit, okay, these are x-intercepts and also called zeros. The reason why they're called zeros is because if I put x equals 3 into here, three minus 3 is 0. 0 times anything is just going to give me 0. Okay, so that's why it's called a 0. Because if I put it in for x, that's what I get. All right? So thinking about that, I look at this and I go, well, gee, what would I put in for x to get 0? Well, I can't because I'm squaring it. And you can't square anything and get added to 1 and get 0. In other words, this I cannot do in the real number system. Okay, so that's why it only has one x-intercept. So when you're doing these, okay, yep, it's a good idea if you can look at them and kind of have a pretty good feel for what the graph's going to look like, but you can always graph them, okay? That's why we use Desmos, is to help us visualize what's going on, okay? So don't hesitate, don't feel bad like, oh, I should be able to look at these and figure out what's going on. Don't be afraid to graph them, all right? So the degree is 3, x-intercepts 3, 0's 3, end behavior as x approaches negative infinity degree is odd, it's got to be decreasing. X approaches positive infinity, it's got to be increasing. Okay? It's got to be. All right?
There's no multiplicity.
There's no what?
Multiplicity.
No multiplicity there. Only when it's on the outside. Okay? On the flip side of that, they're going to give you some of these graphs. And they're going to ask you to write polynomials for them. So you're going to have to go in reverse. But this isn't anything to get too excited. So here we go. F of x equals. Okay, so here's what we got. We got an x-intercept at -2. We got an x-intercept at 1. And we got an x-intercept at 3. Okay? 3 of them. So, what are we going to write? We're just going to go like this. X, intercept at -2, so I'm going to go +2. It's always the opposite. Parentheses. X, intercept at 1, so I'm going to go -1. Parentheses. X, intercept at 3, -3. However, what's happening at 3? What do we got there? What's it doing? Touching and bouncing, right? So that means I have a multiplicity there of 2. Okay, how do I know it's not more? Well, it could be, but I'm going to put 2 there. Right? I don't really know that. It could be a 4. Maybe it's really flat, but I think it's 2. Okay. That's it. That's all you got to do. Okay? Now, what they might do is they might have some numbers sitting out in front here. Okay? I mean, I'm not going to get too worried about that. I guess you could graph this and look to see how close it is to this, matching this thing. Okay? If it doesn't match it, you could change this. Remember that if it's, a decimal, it's going to squish it down a little bit. Okay? But I'm not too worried about that right now because that's going to come in on your project thing anyway we're doing. Okay? Whether you can manipulate the A values. So I'm not going to be too concerned about it in this case. Not important. Not important. That's a lot of what 3.1 is. Okay, it's just looking at graphs, writing equations, or getting equations and writing stuff about the graphs. Okay.
They use real zero and not just zero.
As far as a term, real zero versus not, we're going to do that now. Okay. All right, 3.2. Let's talk about that. Okay, so here's where we're going to start getting into some stuff that has kind of been replaced because of the advent of technology. Okay? I'll go over some of it with you, though, so you kind of know what it is. But I think you'll kind of see, as long as you get a big picture, we're okay. All right. So first of all, let's do this. Let's talk about a second degree polynomial. So if I asked you what would a graph of that look like? Second degree. What are we going to get? Yep. So what's that shape going to be? Good. You're going to get a U. Okay. So, like this. Yeah? Is that good? Like this. Whoops. Yeah? Like this. All those are secondary polynomials. Okay? What's the difference between all of these? What's the only difference? That's right, shifted up and down. Okay. The number of x-intercepts they have. How many x-intercepts does this have? Okay. So a second degree polynomial could have 2 x-intercepts, 1 x-intercept, 0 x-intercepts. All right? Now, I'm going to change colors here for a second. Zeros. 2 zeros, 1 0, 0 real. All right, because 2 real numbers, 1 real number, no real numbers. However, that doesn't mean it doesn't have some more zeros. It's just that they are not real numbers. They're imaginaries with the little eyes. Okay, they're imaginary. Okay, so 2, 1, 0 real. Let's do a third degree polynomial. What's a third degree polynomial basically look like? What letter? Yep. So, we could have this. We could have this. Or we could flip-flop it. But would we ever have one that doesn't cross the x-axis? Could we arrange that n so it doesn't? No. So either we're going to have 3 x-intercepts, we're going to have 3 of them. Okay, we could have 2 x-intercepts, or we can have 1. But there's no way we're ever going to get 0 of them. Okay, this isn't going to happen. All right, so we can have 3, 2, or 1. Zeros, we could have 3, 2, or 1. Okay, 3, 2, or 1. One more, 4th degree. What's a 4th degree look like letter-wise? W. So that, see, did I cover them all? 1, 2, 3, 1, 2, 1, 2, 3, 4, and we could actually just have a 1. Okay, so we can have 4 x-intercepts, 3 x-intercepts, 2 x-intercepts. Did I get a 2, 1? Yeah, here. 1 x-intercept, or 0 x-intercepts. I can have all those situations. On the flips, same thing with the zeros. I can have 4, I could have 3, I could have 2, I could have 1, and I could have 0 real of them. Okay? Okay? So, again, there's a pattern, right? If we have an even degree, then there's always this possibility of not having any x-intercepts, okay? But when I have an odd degree, I got to have some sort of a crossing on the x-axis, okay? It's got to happen, all right? I got to have that, okay? So here's kind of what this is saying, all right? I'm going to talk about the roots. This is going to have 3 x-intercepts, 3 zeros, and 3 roots. Okay? These are all the same thing, pretty much. 1, 2, 3. 3 x-intercepts, 3 zeros, 3 roots. Okay? All the same thing. If this is a -3, and this is a 1, and this is a 3, then we can write this in factored form so it looks like that. Now, I don't know what the a value is, but I don't really care. I just know I can write a polynomial that represents that. Pretty dang close. X plus 1, x minus 1, x minus 3. These are my 3 x-intercepts. Those are my zeros. Those are my roots. Okay? I can write one. So you're going to be asked to do that. All right? It's going to tell you what the x-intercepts and what the roots are. Okay? Now, what's the degree of this? 3. Okay? Good. The degree is 3. That's important because we could also have a 4th degree that has x-intercepts of -3, 1, and 3. And you would say, how would that be? Because how could we change this so that that now has a degree of 4? What would we change? Yep. Now it's a degree of 4, doesn't change the x-intercepts, doesn't change the roots, doesn't change the zeros. It's all the same thing. Okay? We just put a multiplicity there. Doesn't change anything. All right? So now it has a degree of 4. And remember, we just said a few minutes ago, we can draw one that has 3 x-intercepts and it has a degree of 4. Okay? You can do that. You just have to realize that there's a multiplicity there. All right? Okay. Now I'm going to start combining some things in 3. Well, let's do this. Okay. Let's do this. Okay. Okay. So we're going to graph this. Let's find some x-intercepts, which are also zeros, which are also roots. Okay? Go ahead and put that in Desmos, graph it, and let me know what you come up with for x-intercept. Let me know when you get one. I want a nice one. Does it have a nice one?
1.
Perfect. Okay. So what I'm going to do now is we're going to perform a technique on this to see what the other zeros might be, or roots. Okay. Does this just have one x-intercept?
Yes.
Okay. We're going to see what the other zeros might be. All right? Here's how we're doing it. We're going to use something called synthetic division. Now, someplace in your mathematics career, you learn how to do long division with polynomials. Kind of hard in the beginning. Once you got used to it, it gets pretty easy. All right? Synthetic division is another form of that. It's just a heck of a lot easier. Here's how synthetic division is going to work. So we're going to take these coefficients. All right? So I'm going to take 2, -1, 2, and -3. And we're going to divide it by the number 1. Dan says that is an x-intercept. Okay? So I'm going to divide it by 1. So I put this little thing here and divide it by 1. Okay, so here's how synthetic division goes. First thing you do is drop this first leading coefficient down here so that it's a 2. Okay, just drop it straight down. All right, now we're going to multiply 2 and 1 and put that answer right there. So I'm going to take 2 times 1, get 2, and put it right there. All right? Now I'm going to add these. So 2 and -1 give me a 1. There we go. Okay. Now I'm going to take and do the same thing, except this time I'm going to take 1 and this one and multiply those. And I'm going to put the results right here. So that gives me a 1. Now I'm going to add those and I get a 3. And now I'm going to do this again. It's getting kind of messy. And when I add those, I get a 0. Okay? Okay, so big deal. What does that do? What that does is it puts it down into what we call a reduced form. Okay? So now this is 2x squared plus 1x plus 3. 2, 1, 3. So what that means is that polynomial that we wrote can be rewritten as parentheses x minus 1 times 2x squared plus x plus 3. And this is in factored form. Okay? Now this doesn't mean anything to us now, but it will a little later. Okay, so that's in factored form. Okay? If I try any other number besides 1, this is what's going to happen. So if I do synthetic division again, this time I want to pick 2. And I'm going to do the exact same thing. Why did I pick 2? I don't know, just did. Drop this 2 down. 2 times 2 gives me 4. 4 and 1 gives me 3. 2 times 3, that gives me 6. Put that there. Now I'm going to get 8. 2 times 8, 16. Now I get a 13. Okay? The difference is, when I put 1 in there, what did I get here at the end? 0. And now I'm getting 13. Okay? So when we have an x-intercept, we're going to get a 0 here. Okay? So x minus 1 is called a factor of that polynomial because I get a 0 there. Okay? Any other number besides an x-intercept, not going to get a 0. Going to get something else. All right? So let's try some more of this kind of synthetic division stuff here. All right? So let's start off with 1. Let's do x cubed plus 3. I got to be careful with these. X cubed minus 4x squared minus 5. Okay. Graph this, see if it has a nice... Oh, let's just do this. Let's see if x minus 3 is a factor. X minus 3, is it a factor? Well, we can try it. First of all, I'm going to put 3, that's what I'm going to divide everything by. Why would I not put x minus 3? Well, because if x minus 3 is a factor, then that means that positive 3 is the x-intercept. It's the opposite. So now I'm going to do synthetic division. 1, negative 4. I don't have an x, so I'm going to put a 0 there, negative 5. And now I'm going to do synthetic division on this. I don't have an x, so I have to put a 0 in there to hold that place. So, drop down to 1. 3 times 1 is 3. Negative 1. 3 times negative 1 is negative 3. Negative 3. 3 times negative 3 is negative 9. Negative 14. So, is x minus 3 a factor of this? Yes or no? No. Could you have graphed this and checked it out? Yes. Okay? All right? It's not that synthetic division is not useful. It's just that we could have graphed this, checked to see if it crossed that 3, and answered the question without doing this. Okay? So that's the kind of stuff that's in this section. It's going to give you a lot of information, okay? But you don't really need it because you can graph it and answer all of the questions, okay? So for example, this thing is called the factor theorem, all right? And what the factor theorem says, basically, is if you take a, say, well, if you do synthetic division, and the remainder is 0, remainder is 0, then whatever you divided it by, we'll call that the divisor, I guess, is a factor. Now, I'm never going to ask you what the factor theorem says, okay? That's not important to me. But I'm just telling you, that's what's in the book, okay? However, you can use synthetic division or graphing to answer those questions. So if you want to find out, okay, so if I have a polynomial, say this guy, and I want to know, hey, is x minus 1 a factor? Well, I can do one of two things. I can do synthetic division, or I can graph it. Remember, you're always going to divide it by the opposite of that. So here we go. 2, 1 times 2 is 2, 13, 1 times 13 is 13, 6, 1 times 6 is 6. Look at that. I get a 0. So x minus 1 is a factor. Okay, what does that mean? That means I can take and rewrite that as x minus 1 times 2x squared plus 13x plus 6. So this is just this guy factored, okay? That's what it is. But I could accomplish the same thing by just graphing it and looking at it in Desmos and seeing what the factor is. If the crosses, I could have just did that. Okay, so that's what I'm trying to say, is that there's a couple different things going on here that is just we don't use much anymore. Okay. If you have your book on 216, I'm just going to go over a couple things in there. All right. This is on page 216. They talk about two things, okay? They talk about something called Descartes' rule of signs, all right? Descartes' rule of signs. So, in high school mathematics, we haven't taught this in like 10 years, okay? We just don't do it anymore because it's really not very useful. They mention it in here. And all they're saying is this. This is all this says. If I have a polynomial and I perform synthetic division and the remainder down here is negative, and I do it at a number, let's say this is negative 3, okay? Negative 3. Then I try it again at 1. And the number's positive for a remainder. Well, that means that somewhere between negative 3 and 1, there's a root. Okay? That's all it says. But how could I find the answer if I knew what this was in the first place? If I knew what this equation was, how could I figure that out? What would I just do? Just graph it. It tells you. Okay? The graph tells you the answer. You know, Descartes' rule of signs doesn't tell you anything anymore because we can just graph it. Okay? You can just graph it. But you know, years ago we didn't have that kind of technology. You just couldn't graph things. It just didn't happen. So people had to use this kind of stuff. Okay? But I'm not going to ask you to use Descartes' rule of signs. But it's in there. Okay? The rational zeros theorem. This thing's even worse. Okay? Here's what it says. Rational, and again, this is another thing not going to ask you about. Okay? Not going to ask you. Suppose we go back to this guy here. It says that some possible, this is just possible, some possible roots are, we're going to go with 6 over 2. Where'd that come from? 6, 2. So here's what they ask you to do. Write all the factors of 1 and of 2. So that's plus or minus 2. All the factors of 6. Okay? Now, here's some possible roots then. 1 over 1, plus or minus. 2 over 1, plus or minus. 3 over 1, plus or minus. 6 over 1, plus or minus. 2 over 1, we already got that. 2 over 2, we already have that. 3 over 2, plus or minus. 6 over 2, I already have that. And then I have all the rest of those too. Okay? 1, 2, 3, 4, 5. 10 different possibilities I have. Okay? Then I would have to try them all in synthetic division. Okay? That's the kind of stuff we used to do back in the 1970s. Okay? You don't need to do that anymore because all you got to do is graph it. And it tells you where the possible roots are. Okay? So those things are very much just not useful anymore. But they're in here. Okay? And I'm not going to ask you to do that. All right? I'm not going to do it. Okay? So what am I going to ask you to do? Well, here, let's do some problems that I'm interested in you to be able to do. Okay. Let's take this for example. 4x to the 4th minus 15x squared minus 4x, or excuse me, minus 4 is x minus 2a factor. Okay, how would you be able to tell? How would you be able to tell? What should we do with this? Graph it. So go ahead and graph it. Put it in decimals, graph it. Let me know if x minus 2 is a factor. What are you going to look for? What are we going to look for? Does it cross a 2? That easy. All right? Does it cross a 2? So, graph it. Tell me what if it crosses a 2. It does. Yep. What else could I do? I could do synthetic division, okay? If you like synthetic division, you say, this is kind of the neatest thing I've ever seen. And you want to do synthetic division, go ahead. Okay? 4, 2 times 4 is 8. 8 times 2 is 16. 16 and 15 give us a 1. 1 times 2 is 2. 2, 4, 0. Yep. It is. Okay? So you can pick. It doesn't really matter to me. All right? But I want you to be able to look at this and say, I can graph this as a process of 2 that I know this is a factor. Okay? Or I can do synthetic division. I have to have zeros because I don't have an x cubed, I don't have an x. And I can do it that way. All right? That's all we're looking for there. Okay? On your syllabus, did I give you any problems? Does anybody have their syllabus so I know which? I don't think I gave you any in the 21 through 32s, did I? For 224? I don't have one handy, so I don't think I did. Yep. Or, well, it'd be 220, it might be 223. What did I give you on those, that section? 25 through what?
45 through 50.
45? Okay, good. So I skipped the Descartes rule of signs. I skipped the possible zeros. So 45. Okay. So let's look at some of those. All right? So what kind of things are we going to be asked in the... It says, use the rational zeros theorem to find all the real zeros of the polynomials. Why would I want to do that? Why don't I just graph it? F of x equals x cubed plus 8x squared plus 11x minus 20. Okay? It says, I want to find all the zeros, all the real zeros. Okay. Let's check it out. So what should we do to find the real zeros? What are we going to do with that? Graph it. Yeah, graph it. Bless you. So go ahead, type it in. What am I looking for? What am I looking for? I'm finding the zeros. Zeros are the same as? That's right. Same as x-intercepts. Okay? Yeah, I'm just looking for those. All right? Tell me what those are. So graph it. When you get them, let me know.
-5, -4.
There it is. All right? Use it to factor. So now I'm going to write it in factored form. Okay? This is exactly the kind of thing I'd ask you on the final. Okay? Hey, write in factored form for me, would you? Okay. X plus 4. X plus 5. X minus 1. There you go. Thanks. That's what I want. Okay? And that's all you got to do on those. Just graph them. Okay? Find the x-intercepts. Okay? That's what we're looking for. All right? Next thing I want to ask you to do, solve. And here's what they're going to ask you to solve. 2x cubed plus 3x squared plus 2x plus 3 equals 0. Okay? Now, all we're solving is for real solutions. Real solutions. Okay. So, guess what? What are we going to do? Graph it. That's it. You're just going to graph it. Okay? What are we going to look for? There you go. X-intercepts. So, graph it. Tell me what x-intercepts you find. Put it in there. See what you get. That's it. That's the only x-intercepts it has. So that's the only real solution. Okay? That's it. That's all there is. Right? We're just graphing it. All right? Looking for the x-intercepts. See, it's all the same thing every time for all this stuff. Okay. I didn't give you any in the 69, 70s, and that ones, did I? What's the highest we went up to? 79 through 81. There's a 60. I did give you 69?
Yes.
Just cross that one out.
What about the 272 as well?
No, so on 2 through 72, is that what it says?
It says 69 through 72.
Cross those out. Okay. And then I gave you 79?
Yeah.
All right. Okay. So 79 says, this isn't one I would ask you in a test, but I put it on here anyway. It says, use the immediate value theorem to show each polynomial has a 0 in the given interval. All right? So, you're going to graph it, and it's going to ask you, does it have a 0? So, for example, the first one here, x to the 4th minus 2x squared plus 5x minus 1, and it's going to give you a bracket thing like this. Okay? So you want to see if there's a 0 in here. Okay? Well, what are you going to do with that? Yep. And see if there's a 0 between 0 and 1. I mean, you know, that's what this whole thing is. It's all just about graphing and checking things out. It really, you can use synthetic division, but it's so time consuming when you can just graph it and get it. Okay? And we'll use synthetic division, but not for any of this stuff. It doesn't make any sense. Okay? So hopefully you'll see how that stuff works. Okay? I'm going to hand out the second project here, talk about that for a second, and I'll give you some time to work on some stuff. Unless you guys want to just keep going. Yeah, you already know. I'll let you decide what you want to do there. Because it's your assignment time, so it doesn't really matter to me. But let's talk about this, okay? So make sure you turn in project 1. Again, you can submit that way, or you can scan it and email it to me anytime by the end of the day. Project number 2, okay, talks about creating an artistic design using the functions we've learned in this course. You can either search or find something that interests you or create your own. This project can be very challenging, time-consuming, depending on the art you choose. Okay, so anyway, I'll let you read that stuff. Okay, so here's what we got. I'm going to pause this for a second here. Last thing, 3.3. Solving polynomials. All right? Here's the thing that we're kind of noticing here. Third degree, 3x intercepts. I said that could happen. This could happen. Okay? Third degree, but only 1x intercept. Okay? There is a theorem called the fundamental theorem of algebra that says the degree of a polynomial is the number of solutions the polynomial has. That's basically what it says. Use more mathy terms, I guess. Probably more proper English. All right? So if I have a third degree polynomial, dang it. If I have a third degree polynomial, then I have 3 solutions, okay? Not 3 real solutions, but 3 solutions. If I have a 4th degree, I have 4. If I have a 2nd degree, I have 2, okay? That's what the fundamental theorem of algebra says. So, in a case like this, it's pretty obvious. We have 3 solutions, and we can get them by graphing it and clicking on the x-intercepts, right? Now the difference, decimals always does approximate solutions. You know, if they're decimals, it doesn't do exact solutions. So there's a difference there. This one, I can get 1, but these here, where that bump is there, that turning point, tells me there's 2 other solutions, but they're not real. The fundamental theorem of algebra says the degree of polynomial is the number of solutions that the polynomial has. So I need to find all the solutions. And it might specify that they need to be exact solutions. Okay? So, how do we go about doing that? Well, let's take a polynomial. And I'm looking for some good ones here. Solve it. Okay. So we're going to solve this. I'm going to set it equal to 0. All right. First thing I'm going to do is graph it. And I'm going to hope that I have a nice number for an x-intercept. All right. I'm going to hope. Okay. So graph it. See if you can find me a nice number that's an x-intercept. Four. Okay. But that's the only one it has, right? Okay. Here's what we're going to do. We're going to do synthetic division on this. Okay. Remember I said synthetic division is going to help us. Here's where it's going to help us. So, we're going to do synthetic division. Remember, drop the 2 down. 2 times 4 is 8. Negative 8 and 8 is 0. 4 times 0 is 0. 4 times, bring that down, that's an 8. 4 times 8 is 32. And I get a 0 here. Well, I should have got a 0 because I know I'm going to get a 0 here. If I don't, something went wrong, okay, in your synthetic division. You got to get a 0 because you just graphed it and figured out that it was an x-intercept. What does that mean now? That means that this is now in reduced form. So 2x squared plus, I'm just going to put a 0x there just so you can see where that comes in, plus 8. Okay? So if I factored it, this is what it would look like. So what I want to do now is solve this. Okay? I need to solve that thing. All right? Here's the good news. I know how to solve this. I could set it equal to 0. Divide by 2. Square root Now you're saying you can't take square root of a negative number. You can in the imaginary system. So the other two solutions are imaginary. Okay? So we graphed it. We found a nice number. Used synthetic division to put it in reduced form. Okay? Now we took that reduced part of it, set it equal to 0, and solved it. And now here's my other two answers. Okay? They might have you do this and write it in complete factored form. What was that for? There we go. Now, that's in complete factored form. Okay? That's how you solve these all the way. You find one, you graph it, find one nice x-intercept, do synthetic division, and then solve it out. Okay, let's try another one here. Three x cubed. Where'd it go? Oh, I don't want that one. Here was, oh. Dang it. They didn't give me any x cubed ones here. Let's try this one out. Negative 4x cubed minus x squared plus x plus 2 equals 0. Okay, graph it. We're going to solve this. Hope it has a nice x-intercept. Is that the only one?
Yeah.
Crap. We don't want that one then. It's got to be a nice x-intercept. I thought that one would from what was given in here. Okay. Here, let's do this one then. What about this one? 2x cubed minus 14x squared oh, God dang it. I'll just have to do a fourth root. Sorry, folks. We can do a fourth. 3x to the fourth plus 5x cubed plus 25x squared plus 45x minus 18 equals 0. Okay, we can do one of these. All right, let's do it. Find me a nice x-intercept, I hope. Unless I wrote it down wrong. 3, 5, 25, 45, 18. Nope, should be okay.
-2.
-2. Is there another one?
Yes, it's 0.333.
0.333?
Yeah.
Okay. 1/3. All right. So here's what we're going to do. We're going to do synthetic division on this. Divide it by -2. Okay, so I'm going to divide it by -2. There's the 3. 3 times -2 is -6. -1. 1 times that is 2. 27. -2 gives me -54. Oof. I'm going to get a 9. 9 times -2. No, this is -50. This is positive 50. What happened here? No, it's a -54. This isn't working out. You said -2, right?
Yes.
Yeah, it works out. Positive 18 equals 0. Okay, it works out. All right, so there we go. All right. So, got a 0. That's what I was worried about for a second there. This is now in reduced form. We started with an x to the 4th, so this is going to be 3x to the 3rd minus 1x squared plus 27x minus 9. Okay? But that's a cubic. We got to get it down into a quadratic because I can solve those. All right? So guess what? We're going to do synthetic division again, this time with 1/3. Okay? So these ones you're going to do synthetic division twice. All right, here we go. 3, 1/3 times 3 is 1. Here, let's just, let me rewrite it down here so I have it. Coefficients. Okay, there we go. 1/3. So 3, 1, 0, 0, 27, 9, 0. Now I have it as a quadratic. I don't have any x's. I can set that equal to 0. Solve it for x. Boom, boom. X squared equals -9. Square root. X is equal to plus or minus 3i. Okay, so here's my solutions. Here's a solution. And 4, I think. Was it 4? No, -2, right? Those are my 4 solutions. Okay. Those are my 4 solutions. That's how we do those. You got to graph them, find a solution, use synthetic division, break it down to a quadratic, solve the quadratic. Okay? Solve the quadratic. Here's one thing that we know. This is going to have 3 solutions. Okay? If one of them is a real solution, then the other 2 have to be imaginary. So, if A plus BI is a solution, automatically A minus BI must be a solution. And that's in your book too. So you can't have one imaginary. You got to have 2. All right? You can't have just one. If you have one, you got to have the other. Those are conjugates of each other. You got to have 2. Okay? So every time you get one imaginary, you know you're going to have 2. You got to have it. And that's the end of that section. All right. Here's one where they say the degree is 4, and they want you to write a polynomial in factored form. And the solutions are, zeros are 3 and 2 minus I and 1. Okay? So, we're missing 1, right? Because the degree is 4, and we should have 4. What's the other one have to be?
2 plus I.
Yep. Because if 2 minus I is a solution, 2 plus I has to be a solution. Okay? We can write this in factored form now just by doing this. Okay? 2 minus I, parentheses, x minus 1, parentheses, x minus 2 plus I, parentheses, parentheses. There it is. Okay? Hopefully they never ask you to put it in general form, because that would be a real mess. All right? So as far as I'm concerned, you can just write them in factored form. You don't have to write them in general form. They probably will. All right? When it's a 4th degree like that, it's a real mess. You can do it, but it's kind of a mess. Okay? But that's it. That fundamental theorem of algebra is pretty key. Okay? So like on the final, I'm going to ask you to solve some. The nice thing is they're going to work out. Okay, so you're going to find an x-intercept, use synthetic division, break it down into a quadratic, and then solve it. You can use a quadratic formula on it. Sometimes that's best, depending on the quadratic. These were pretty simple, and that's one the ones I looked at in the assignment kind of did that. So, all right, that. Do you have any questions on any of that stuff then? Anything we did there? It's a lot.
Will there be any questions that don't have any real?
As far as solving them?
Yes.
Can't. Because you don't have any way, nothing to go on.